Hi, my name is Soumyadeep, and today we're going to be talking about index-only scans and covering indexes for GPDB 7. So let's begin with index-only scans. The key idea behind an index-only scan is that if you have a query like this, select I from T where I less than 20, where the index column, which is I here, and the kind of the projection list contains the same kind of columns, or a subset of the columns that are being used for the predicate, um, you should be able to return the results from the index relation file without consulting the table relation file. You do not need to go and visit the table relation file at all, which is what an index scan would have done. In here, you just look at the index rel file itself, where all the information is kept to answer the query, and just return that information. That's the basic idea. And in doing so, you save on a lot of I/O, right? Especially if you have a wide table. A wide table is a table which has the total length of each tuple is pretty high. This could be because of the number of columns or because you're having a lot of long fields in that schema, right? So wider it is, the number of blocks, the tuple density in the blocks would be lower, and you'd have to scan more blocks from the base table. Um, this is where you would win more significantly if you have an index-only scan going for you, right? And now, heap and append-optimized row-oriented tables, this is going to be especially useful. Less so for column-oriented tables because we already have the column projection pushdown, which limits the amount of stuff that you have to, the amount of data that you have to scan from disk. But again, if you're doing a very highly selective query, then even for an AO column, it would be beneficial because the column projection pushdown does not involve, you get the benefit of the index to do the filtering, but that you will not get from the column projection pushdown, right? So um, the other thing about IO wins is that the disk access pattern is much better. All you need to do is look at the index file, whereas for an index scan, you'd have to go back and forth between the index and the table file on disk. That's not great. That's even worse for column-oriented tables because you have more relation files because each column is maintained as a separate file. Furthermore, you are not doing any random access into the table file, which is a big deal. Um, especially so much so, especially it's a bigger deal for append-optimized tables. It's very inefficient for append-optimized tables. It's so inefficient that we typically disallow index scans on them. The only thing that we allow is bitmap index scans, which has a nice ordering property in terms of access pattern. So that's something to keep in mind. So there are significant wins there. Now, not only I/O wins, we also have CPU wins. The first CPU win that we can talk about is the tuple deformation overhead that we save on, right? If you have a if you have a um, if you have a heap table or an AO table, there it is. Each tuple is kept in a specific format on disk. It's an on-disk format, and that on-disk format is complex to extract data out from, right? There's a lot of there can be a lot of branches. It's an involved process. There are a lot of conditions, a lot of things that you have to look at: types, data types, variable length types, etc. It's not very friendly for branch predictions and so on. And to optimize, in fact, it is so significantly expensive. We even have a feature in GPDB 7, which is jitter tuple deforming, which helps you save on it, right? Which helps you optimize tuple deformation. Here, on the other hand, you do not have to do any kind of tuple deformation at all, right? All of the datums that you need to serve your query is already kept inside the index. Now, for AO row and AO column tables, there's another win for CPU, which is there is no block decompression. Naturally, append-optimized tables are usually highly compressed, right? So if you're doing random lookups for for like an index scan, right, you'd have to look up the tuple from the index in the relation file, in the base relation file. When you do that, imagine you look up one tuple. So to do that, you have to decompress a var block for the AO table, and you extract one tuple, right? The next tuple might not even map to the same var block, and you'd have to open up another block and you have to decompress that one. And you didn't get the benefit of, or any caching benefit from the previous block that you just decompressed. So it's very, very inefficient. You get to avoid all of this with an index-only scan, right? So quickly, what are the indexes that have enough information to even support an index-only scan? B-tree-gist and SP-gist, because they maintain the per tuple information necessary. The other ones, they do not, right? So one thing, though, that we have to be mindful about is visibility checking for each tuple, right? Each in MVCC land, Postgres and Greenplum, you need to check the visibility of every tuple that you return. Otherwise, you'd be returning wrong results in the transaction context that you're in the specific transaction context that you're in. So you need to look at some visibility information. Now, indexes do not maintain any visibility information. They just maintain, usually like a B-tree index, it just maintains pointers to the tuples in the base relation file, right? And the tuples themselves in the base relation file, they have the system columns xmin, xmax, which can be used to answer visibility checks, right? But now we are not even going there. So what's going on, right? What do we do exactly for visibility checking? Well, when you get a tuple reference from an index, you basically have it contains a block information along with the offset inside the block for a heap table, right? Let's talk about heap tables first. So from that block, what we usually do first is to for an index-only scan, we go and check if that block is marked as all visible in the visimap for the heap table, which is a very compact structure on disk, right? Which can help answer this kind of a thing. Now, if a block is marked all visible, that means all of the tuples inside that block are visible. And you don't need to do anything further. You don't need to look at the block on disk. You don't need to scan it. You don't need to process it. You don't need to do anything. You're done, right? That's a best case. However, if that block is not marked all visible, then you need to scan the tuple from the table and then check the xmin and xmax columns. Now, that can be an expensive operation, right? So that's not, then you might argue, hey, that's not a true index-only scan. You're actually looking at the table relation file in addition to the index. So that's something to keep in mind, right? And actually, we have a rel stat, which is PG class rel all visible, which is actually like rel pages and rel tuples, which are also present. We have rel all visible, which is the number of blocks that are all visible, right? And if you divide this by rel pages, you'll get the fraction of blocks that are all visible, right? Out of all the blocks in the relation. Now, this is used as a costing parameter for index-only scan. The best case as you can already think of, is if rel all visible is equal to the number of relation pages, rel pages, right? And if that is the case, then you never need to scan any tuple from the table. But the worst case, which is rel all visible equals 0, which can happen if you never vacuum the table. If that is the case, then we don't have enough information. The visimap doesn't have enough information to satisfy a visibility check. So you need to go and scan the tuple from the table, each and every one that is present in the index. And your index-only scan is no longer an index scan. It is no longer an index-only scan. It's now an index scan. That's bad, right? And typically, the optimizer will prevent picking index-only scan, or even if it does, it'll just operate like an index scan. So you won't get the benefits out of it. No, you won't get as much benefit out of it. You will still get benefits out of it just by virtue of the index being picked, but you won't get the index onlyness that you're looking for, probably. So to keep this statistic populated, what you have to do is run vacuum full, cluster, alter table, all of these things will populate rel all visible. Now, if you're just running analyze, run vacuum analyze instead of analyze. That'll work, right? So this is something to keep in mind. And I'll talk about like what to do with vacuum and all that in a little bit, what the best practices are. But let's see how this looks like, right? So this is what an index-only scan looks like. So this query is a very simple query. We are selecting the 5 most recent shipping dates from line item. So this is like select ship date from line item, order by L ship date limit 5. And what you see that you have the index only scan here picked, right? And what is interesting, there's a little parameter here from the explain analyze output, which is heap fetches 5. So we're fetching 5 rows out. Heap fetches 5 means all of these 5 rows had to be looked up in the base table. So this isn't truly an index only scan. We had to go and fetch those 5 tuples from disk to satisfy the visibility checks, to perform the visibility checks. And that is expensive. And as you can guess, this table was not vacuumed. And that is why we had heap fetches 5. Otherwise, we would have had heap fetches 0. So obviously, this is too small of an example for this to have any effect. Like if you are operating on more data, you're doing more fetches, etc., that is when the cost is going to come in. So visibility checks for AO tables, well, it's slightly different from heap tables. This is because AO tuples do not contain visibility information. They do not contain any system columns for that matter. And furthermore, they do not have any concept of all visible, right? What this means is that we never have to scan the underlying table to perform a visibility check. However, we have to look up a couple of auxiliary heap tables that we maintain for each and every append optimized table, which is the VisiMap and the block directory. And we need to perform 2 lookups for each tuple from the index, right? Now, each of these random lookups that we perform is very, very expensive. And the reason is that each random lookups consists of an index scan start on the VisiMap relation. The VisiMap relations themselves are indexed as well. And we fetch one tuple from it, and then we end the scan. And we repeat this procedure for each and every lookup that we have, for each and every tuple, and consequently each and every lookup that we perform. Very expensive, this is. So we don't pick index-only scans as often for AO row and AO columns. Unless there are, I mean, we won't aggressively pick this operation unless other factors are met. One of the factors being that if the table is clustered on a specific column and you have an index on that column, and what that means is that pgstats.correlation for that column is pretty high, and your values for that particular column increase or decrease consistently with the increase in block numbers in the base table. If that is the case, that means if your VisiMap and block directory lookups, the per tuple lookups that I was talking about, are less random, and we have caching in play for those lookups now, because you'll get more cache hits for the block directory and VisiMap. Specific caching that would involve even doing the scan. You can just look up the last block directory mini page that we scanned. So this is significant savings in play here if you have clustered. So if you have a clustered index, and that is why we prefer clustered indexes when it comes to index-only scans. So let's look at some performance experiments. We're doing a very simple experiment here with Planner and a local workstation, so nothing crazy, nothing elaborate, and demo cluster with 3 segments and no mirrors. All default GOCs, default workmem, default shared buffers. We're using TPC8 scale 30 and a mixture of primary keys, composite keys, and some clustered indexes for the B-tree indexes. Nothing fancy. And what happens ultimately at scale 30 for heap tables is that you will see that the blue bar indicates without iOS and the red bar indicates with iOS. And you can see that we get some significant benefits here. Query 4, Query 17, Query 18, Query 21 have all benefited from an index-only scan being picked. And let's just drill into some of these, right? So Query 4, right? Query 4, this is the part of query 4 that we're trying to optimize here. The line item table is the fattest table in TPC 8 scale 30. I think it takes up 26 gigabytes. So let's concentrate on that one, right? So what we do is we create a composite index as well as a partial. This is a partial index, as you can see, with the little condition here. And this is the part of the query that we're trying to optimize with an index-only scan. So let's look at the query. Let's look at the explain analyze output without an index-only scan. So you can see without the index-only scan, this takes around 59 seconds. And yet you have a sequential scan on line item with this filter, and lots of rows are being removed and unnecessary work is being performed, right? This itself is taking around 22 seconds to do the sequential scan. Now, if you vacuumed all of the tables, in specifically line item, then index-only scan would be picked. And you will notice that this only takes around 9 seconds. And we get significant savings with respect to execution time. Also notice heap fetches to 0 because this table was loaded once and then vacuumed once, and that set the rel all visible equal to rel pages. Let's look at another query, query 17, right? And in query 17, this is the part of the query that we're trying to optimize. Again, we have another composite index on these columns specifically. And let's see what it looks like, right? So without an index-only scan, notice that we have a partial hashtag and underneath a sequential scan on line item, right, to answer this. So you'll notice that the partial hashtag takes around 126 seconds, and the sequential scan here takes 11 seconds, right? Now, if you notice with iOS, and if you ran the vacuum, what happened is the hashtag turned into a group bag, and the sequential scan turned into an index-only scan. Now, the index-only scan is due to variations in runtime, and so this 19 seconds versus the sequential scan is 11 seconds. You can kind of hand wave it out, even though this is maybe a little bit expensive. This could be due to variance and so on. Notice how different the partial group bag is with respect to the partial hashtag. This is 126 seconds versus 46 seconds. So this is the big win here. And what we're doing is we are transforming a hashtag sequential scan into a group bag index-only scan. Now, the index-only scan here is being used is also serving the purpose of ordering, right? To perform a group bag, you actually need the input to the group bag to be sorted. And the index-only scan, the index is actually being used to sort for the group bag. And there's a link to an article here, and you can look at it at your leisure. That is, group bag and index-only scan is a very nice combination, especially when the number of groups is pretty high, because sometimes you won't be able to fit a hash table in memory, whereas a group bag would fit very nicely because you only need to keep the last group around in memory. So that's a big win right there. This is an interesting aspect that the index-only scan is actually using, it's influencing other execution operators around it. That's an interesting thing. So let's talk about best practices, right? So if you have a read-only table, or if you have a read-only heap table, just vacuum it once after loading it. And if you don't do this, again, rel all visible will be 0, and index-only scans won't be even considered, right? So this is a must do, right? Now, if you have regular updates and deletes, your ETL coming in and so on, run this after that, and that will also ensure that PG class rel all visible reflects reality. And if you have an AO and CO table, now this gets a little bit more nuanced. Vacuuming AO and CO tables is not as important as heap tables because there's no concept of rel all visible. However, running vacuum on AO and CO tables has the benefit of removing block directory and visimap bloat, which are themselves heap tables, right? You keep them lean. They are pretty lean anyway, but keeping them more lean is not bad. And if you want to squeeze that bit more out of your tables, what you could do instead of running vacuum on the entire table. So if you run vacuum on an AO or CO table, it'll vacuum the AO and CO table as well as its auxiliary tables. But if you just want to vacuum the auxiliary tables, one option you have is if you're running auto vacuum, you can set GP auto vacuum scope to catalog AOX, which means that apart from the catalog tables that is the default for auto vacuum for Greenplum 7, it will also go and auto vacuum any auxiliary tables. So that's one way of achieving that. For append-optimized tables, if you have clustered indexes, you're in a better position to have the index-only scan picked. Now we do have a room to improve for non-clustered cases, which we'll be working on in later minor releases, which is cost model improvements to pick or not pick index-only scan, and execution improvements as well for reducing the block directory map overhead that I talked about. Now let's delve into covering indexes, which is quite a related feature. So again, the objective of covering indexes is to achieve index-only scan in certain queries, right? And here, you have some extra columns apart from the index columns involved. Like for example, select I, j from T where I is less than 20. J is an extra column here. Similarly, select J from T where I is less than 20. I is the index column, whereas J is what is called the payload column. If you have queries like this and you want to optimize, and you don't want to go and fetch stuff, if you have an AO table, you don't want an index scan. You can't have an index scan, for instance, right? You can have a bitmap index scan, but again, if you want to do the optimization, if your table is read-only, this might be an interesting thing to do, especially if you analyze your query access patterns and you find that whenever you're operating on I, you're also projecting this other J, right? So this is something to keep in mind. And if you have this kind of a thing, what you can do is you can create a covering index. What it is basically just use this include clause and just specify whatever extra payload you want to be stored along with your index key. And it'll actually store it in the index itself, right, as a payload. And with this, if you do this, then an index-only scan is going to be picked for queries like this, right? But wait, right? What about composite indexes? Like, what if you created an index that looks like this, as opposed to an index that looks like this, right? What's the difference? When should we use composite indexes versus covering indexes? Because in my previous examples also I used composite indexes, and that was used to pick an index-only scan in my previous examples, right? So both of them can help you get index-only scans, but which one do you use, right? And under what conditions? Well, if you want flexibility in terms of filtering, like you want things like this: select I, j from T where J is 20. You want to use the extra column as a part of your filter, then composite index is good. If you are absolutely sure that this is not going to be used for filtering, J is not going to be used for filtering, then and only then should you use a covering index, because in the covering index, J is never going to be able to be used for a filter, right? So that is something to keep in mind. Now, there are certain things that is achievable only with a covering index. Like you have a unique index on, let's say, I, and you always have a query where you are either where you're where you're selecting data on the basis of I, but you're also wanting to project J from the table. In this kind of situation, you can only achieve this kind of thing, an index-only scan, with this syntax. There's no way to do this with a composite index, because if you create a unique index on Ti and J, that means a very different thing. It means the uniqueness is being imposed on both I and J, as opposed to just I over here, which are semantically different. Also, covering indexes, one of the interesting things is that the payload columns need not be of an indexable data type because it's just pure cargo. There's no logic to query on the basis or to filter on the basis of it. Whereas extra columns here must have an indexable data type that must have an op class and so on, right? So that's also an interesting distinction. Finally, payload columns are always omitted from the upper pages of a B-tree index. So this is an interesting optimization that's available with Greenplum 7. Um, some of the upper pages of a B-tree index do not contain payload columns. And if you use the include syntax, that is a surefire way of achieving that. Whereas if you use a composite index, it will sometimes be omitted from the upper layer. So this is just a small tidbit about optimization in terms of the size and footprint of the upper layers of a B-tree index, the interior pages, the root page, and so on. So let's look at query 10 as an example of how we can apply a covering index, right? So you have this, again, let's talk about line item, right? Line item, we have certain filters here, order key, return flag, and we are trying to aggregate on extended price and discount, which are two other columns, right? So what we do is we create this covering index on line item order key, and we're including the extended price and discount as cargo. And what we're doing is we are also doing like a partial index on return flag, which is interesting, right? So we have this index set up here. Now what will happen is if you don't have all this index set up, you end up with around 38 seconds of runtime. Your sequential scan gets picked and a lot of wasted work, a lot of wasted effort, right? But with the covering index, you have the index only scan picked and you get a nice execution time bump, right? Just 3 seconds of execution time for the index only scan. One other thing to keep in mind is that if you have an expression index and your expression involves a function expression, like for example, we have an index on discount, on the ceiling of the discount value, right? Discount is a numeric. And if you have this, and if you have a query like this, explain select L discount from line item where the ceiling is less than blah, right? If you have this kind of query, logically, theoretically, in principle, you should be able to use a index-only scan. The system should be able to use an index-only scan to satisfy this query, but unfortunately, it's not able to. The planner isn't smart enough to actually figure out that we can just use an index-only scan on L discount, right? However, if you were to help the planner out a little bit by including this column right here as cargo, it actually is able to figure it out. It is actually then able to use the index-only scan, as you can see. So something to keep in mind when dealing with function expressions. This is also another point of improvement. Ideally, you wouldn't need to include this extra column here, but for now, you would have to. Again, for best practices, all of the best practices for index-only scans apply here, right? And you would want to prefer covering indexes to composite indexes when there is a guarantee that the payload won't be filtered on, right? That's the one thing to keep in mind. And do remember that stuffing more columns into the index will make it fatter. B-tree indexes are fat anyway for OLAP. There is going to be a size increase. So if you can tolerate that, if your application can tolerate that, great. If the table is read-only, then really good, right? So yeah, so something to keep in mind is like, for example, for the query 10 index, without the payload, it's 1532. It's with the payload, it's 1532, whereas without the payload, it's just 850. So you can kind of see what the size difference looks like. So I'll leave you with a few references. The Postgres documentation is actually pretty good. Very, very good, in fact, with detailing all of these things. And you can kind of read about multi-column indexes and index-only scan and covering indexes and so on. And with that, I will conclude today's discussion. Thank you.